Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group. I will teach you Power System 1.
Next, we solve a problem. A single core cable has a conductor diameter of 1 cm and internal sheath diameter of 1.8 cm. If impregnated paper of relative permittivity 4 is used as the insulation, calculate the capacitance for 1 km length of the cable. Now here it is given that mu r is equals to 4, length is equals to 1 kilometer, conductor diameter small d is equals to 1 centimeter, sheath diameter is equals to 1.8 centimeter. 1.8 centimeter. So what is the formula of capacitance of cable? Now the formula of capacitance of cable is C equals to epsilon r L 41.4 log 10 d by d. Here is a mistake. This is equals to 10 to the power minus 9 farad per meter, and this is 10 to the power minus 9 farad. So at first this is we convert here the length of the cable is in meters, we convert into meter, and now putting the value of epsilon r is 4, length is 1000, 41.4 log 10, d is 1.8 and small d is 1, and by putting the value of these we get 10 to the power minus 9. So putting the value of epsilon r L, capital D and small d, the value of capacitance is equal to 0.378 into 10 to the power minus 6 farad, or we can say 0.378 microfarad. This problem is calculate the capacitance and charging current of a single core cable used on a 3-phase 66 kV system. The cable is 1 km length long, having a core diameter of 10 cm and impregnated paper insulation thickness 7 cm. The relative permittivity of the insulation may be taken as 4 and supply frequency 50 Hz. So we calculate the capacitance and charging current. Now what is the value of epsilon r? It is given 4. What is the value of small d? It is given 10 cm. And what is the value of capital D? Capital D is small d plus thickness into 2, because capital D is equals to thickness of the sheath equals to total diameter of the conductor plus thickness of this side and thickness of this side. So so capital D is equal to small d plus thickness into 2. So what is the thickness? Thickness is 7 centimeters. So small d plus 2 into 7, 10 plus 14 equals to 24 centimeter. So capital D is 24 centimeter. And what is the value of length? Length is 1 kilometer or 1000 meter. So from here C is equals to epsilon r L 41.4 log 10 d by d into 10 to the power minus 9. So this is equals to 4 into 1000. 41.4 log 10, capital D is 24 by 10 into 10 to the power minus 9, and which is equals to 0.254 into 10 to the power minus 6 farad, which is equal to 0.254 microfarad. Now voltage between core and sheath. Now next we find the expression of charging current. So we have to find the voltage between core and sheath. So voltage between core and sheath is equals to 66 by root 3 equals to 38.1 kV. Now what is the formula of charging current? Charging current is equals to V phase by XC. What is XC? V phase by 1 by 2 pi FC. So this is equals to 2 pi FC into V phase. So this is equal to 2 pi. F is given 50 Hz into C 0.254 into 10 to the power minus 6, and this is 38.1 into 10 cube. So what is the value of charging current? Charging current by is equals to 3.04 ampere. So what is the value of capacitance? Capacitance is equal to 0.254 microfarad, and this is the value of charging current. Next one is dielectric stress in a single core cable. Dielectric stress in a single core cable. Now under operating condition, the insulation of a cable is subjected to electrostatic forces. Now this electrostatic forces is known as dielectric stress. The dielectric stress at any point in a cable is the potential gradient or electrical intensity at that point. Now consider a single core cable with diameter small d, and the internal sheath diameter capital D. So internal D, and the internal sheath radius is capital D by 2, and internal core radius is small d by 2. Now the electric intensity. Now the electric intensity at a point x meters from the center of the cable, x meters from the center of the cable is equals to q by 2 pi epsilon 0 epsilon r x volts per meter. Now by definition of electric field intensity is equal to the potential gradient. So G is equals to electrical field intensity, where G is the potential gradient at a point x meters from the center of the cable. So we can write G is equals to Q by 2 pi epsilon 0 epsilon r into x. Unit is volts per meter. Now potential difference V between conductor and sheath, we have already derived this expression Q by 2 pi epsilon 0 epsilon r log E capital D by small d volts. And what is, determine the value of Q equals to 2 pi epsilon 0 epsilon r into V by log D by D. This is our expression 2. Now substituting the value of Q in expression 1, we get, put the value of Q now this term is cancelled out. Now this is our equation 3. Now it is clear from the equation 3. Now it is clear from the equation 3 that the potential gradient varies inversely at with the distance x. Therefore, potential gradient will be maximum where x is minimum, and potential gradient will be minimum when x is maximum. So when x is at d by 2 or at the surface of the conductor, we get the maximum value of the potential gradient, that is G max. And when x is at d by 2, that is x is at highest, we get the lowest value of the potential gradient. So G max is equals to V by, put small d by 2 in place of x, small d by 2 log E d by d. So what is the value? And put the value of x, capital D by 2 at G mean. So what is the value of G max? G max is equal to 2V by small d log E by d by d, and G mean is equals to 2V capital D log E d by 2. Now what is the ratio of G max by, so what is the ratio of G max by G mean is equals to 2V by D log D by D by 2V D log D by D. So this is equals to capital D by small d. This is the very important expression. G max by G mean equals to capital D by small d, that is diameter of the sheath by diameter of the conductor. It is clear that the dielectric state is maximum at the conductor surface, and its value goes on decreasing as we move away from the conductor. It may be noted that maximum stress is important consideration in a design of a cable. For instance, if a cable is to be operated at such voltage that maximum stress is 5 kV per mm, then the insulation used must have a dielectric strength of at least 5 kV per mm. Otherwise, the breakdown of cable will become inevitable. Now we solve a problem. A 33 kV single core cable has a conductor diameter of 1 cm and a sheet of inside diameter 4 cm. Find the maximum and minimum stress in the insulation. So what is V equals to 33 kV, small d is equals to 1 centimeter and capital D, that is sheet diameter, is equal to 4 centimeter. Now what is the formula of Gmax? Gmax equals to 2V by small d log d by d. Now put the value of V, we get, put the value of V small d and capital D. This equals to 47.61 kV per centimeter. Now the value of V is in kV and D is in centimeter, so the unit is kV per centimeter. So Gmax, the maximum stress that is occurs at the conductor surface, and the value of it is 47.61. So what is Gmax? Gmax is the maximum stress occur at the conductor surface and its value is given by 47.61 kV per centimeter. Now what is the value of G minimum? G min, what is G min? This is the minimum stress occur at the sheath and its value is given by 2V by capital D log E D by D. So put the value of V, capital D, small d, we get the value of G minimum is 11.9 kV per centimeter. Or alternatively, as we already determined the value of G maximum, so from this expression we also get the value of G minimum. Okay, G maximum is 47.61, capital D is 4 and small d is 1. So from this we also get the value of G minimum. This is the alternative way. Another problem, the maximum and minimum stress in the dielectric of a single core cable are 40 kV per centimeter RMS and 10 kV per centimeter RMS respectively. If the conductor diameter is 2 centimeter, find the thickness of insulation and operating voltage. So G value of G maximum is given 40 kV per centimeter and value of G minimum is given 10 kV per centimeter, and small d is also given 2 centimeter. Conductor diameter is 2 centimeter. So what is capital D? We know this formula, G max by G min equals to capital D by small d. So what is the value of G max? 40 by 10 into D by small d So this is 4 into 2 equals to capital D equals to 8 centimeter. So what is the thickness of the insulation? Now, as in previous case, I have told you that capital D is equal to small d plus 2 into thickness. Small d plus thickness of this side plus thickness of this side is the thickness of the sheet. So d is already given, that is 2 plus 2 into thickness, and capital D we just calculate the value, that is 8. So thickness is 8 minus 2 by 2, that is our thickness, which is 3 centimeter. Okay, now we determine the value of voltage. So from the formula, V is equal to G max small d log E small capital D by small d by 2. So by putting the value of G max 40 into small d into log 8 by 2 by 2, unit is kV, we get the value of operating voltage 40 kV per RMS. So this is the thickness and this is the operating voltage. Next is the most economical size of the conductor. Now it is already discussed that the maximum stress in a cable occurs at the surface of the conductor, and for safe working of the cable, dielectric strength of the insulation should be more than the maximum stress. Now what is G max? G max is equals to 2V by D log E D by D, unit is volts per meter. Okay, now the values of working voltage V and internal sheet diameter D have to be kept fixed at certain values due to design consideration. Now this leaves conductor diameter D to be the only variable in this expression, and the most economical conductor diameter will be one for which G max has a minimum value. So the value of G max will be minimum when D log E D by D, this term is maximum. So if this term is maximum, then G max is minimum. So for maximum value of D log E D by D, we derivative it with respect to small d, that is the conductor diameter, because this is the only variable, and the first derivative should be equals to 0, so we get the maximum value. So this is equals to log d by d, because this is 1, plus d into d by d into minus d by d square equals to 0. So from here log E d by d minus 1 equals to 0. So log E d by d is equals to 1. So d by d is equals to e to the power 1, that is 2.718. So most economical conductor diameter. So most economical conductor diameter when D is equal to capital D by 2.718. From this we can write this. Now and the value of Gmax under this condition is Gmax is 2V D, and this is equals to 1. So Gmax in this condition is 2V by D volts per meter. Now for a low and medium voltage cable, the value of conductor diameter arrived at by this method is often too small from the point of view of current density. Therefore, the conductor diameter of such cable is determined from the consideration of the safe current density. For high voltage cable, designs based on the theory give a very high value of D, much too large from the point of view of current carrying capacity, and it is therefore the advantageous to increase the conductor diameter to this value. Now these are three ways to doing this without excessive copper. First one is using aluminium instead of copper, because for the same current, diameter of aluminium will be more than that of a copper. Next, using copper wire stranded round a central core of hemp. Third one is using a central lead tube instead of hemp. Now we solve problems. The first problem is find the most economical value of diameter of a single core cable to be used on 50 kV single phase system. The maximum permissible stress in the dielectric is not to exceed 40 kV per centimeter. Peak value of cable voltage which is equals to 50 into root 2 equals to 70.7 kV. Now maximum permissible stress is given by 40 kV per centimeter. Now assume this is the peak value. So the most economical conductor diameter is small d 2V by G max, which is equals to 2 into 70.7 by 40, that is equals to 3.53 centimeter. So this is the most economical conductor diameter. Next problem is find the most economical size of the single core cable working on a 133 kV three-phase system if dielectric stress is 60 kV per centimeter can be allowed. Now first we determine again the phase voltage. Phase voltage, that is V by root 3, that is equals to 132 by root 3 equals to 76.21 kV. Now peak value of the phase voltage. Now peak value of phase voltage is equal to root 2 into 76.21, that is equals to 107.78 kV. Now G max is given 60 kV per centimeter. So most economical size of the conductor 2V by G max 2 into 107.78 by 60, that is 3.6 centimeter. Now internal diameter of sheath, internal diameter of sheath, that is capital D, is equals to 2.718 into small d, that is equals to 9.78 centimeter. So the cable should have a conductor diameter 3.6 and internal sheath diameter 9.78 centimeter.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.